Section 2.4, Polynomial Division. Now in the last lesson we talked about solving polynomials of higher degree. We already knew how to solve linear functions and we had some basic ideas on how to solve quadratic functions. And then we started to generalize all the different techniques for solving any random polynomial function. We talked about greatest common factor, we talked about quadratic techniques that can apply not only to quadratics but anything of a quadratic form. We talked about grouping. The one thing that we did not talk about in the last lesson, which is what we're going to talk about in the next lesson, is the rational root theorem. That's kind of like your last ditch effort. Nothing else worked, so let's try the rational root theorem and hopefully that will work, but even that is not guaranteed. The rational root theorem, though, requires a technique that we need to talk about now, which is polynomial division. So in this lesson, our goals is that the student will be able to divide polynomials using long and synthetic division. Students will be able to evaluate functions using the remainder theorem, and students will be able to confirm factors using the factor theorem. So most of the lesson is going to focus on the techniques of dividing polynomials, long and synthetic division. We're going to spend a little bit of time on long division and then immediately realize that long division is a waste of time, and we'll just jump into synthetic division because it no matter what your Algebra 2 teacher told you, synthetic division does work 100% of the time. There is no situation where synthetic division does not work. At the end of the lesson, though, we're going to put polynomial division to work with the remainder and factor theorems. And with the remainder and factor theorems, those theorems themselves are going to lead into what we're going to do with the rational root theorem, because the rational root theorem depends on these two theorems as support. Without these two theorems, the rational root theorem doesn't make any sense. So, as I said, we're going to go ahead and start with long division because we have to eat our vegetables sometimes. The long division algorithm is kind of foundational to what's going to come after, and it's helpful to go through this. Not only does it give us an appreciation for synthetic division, but I think it really helps us understand why synthetic division works. So as always, let's look at the first one together to kind of refresh you on how to do it, and then I'll give you the second one to do on your own. So remember just some basic vocabulary. The numerator, the top, is actually called the dividend, and the denominator, the bottom, is actually called the divisor. And of course, when we divide the dividend by the divisor, we get a quotient. And if it doesn't divide evenly, then we're also going to have a remainder. So let's go ahead and set up our long division problem. Remember, with a long division problem, we got this doodad right here. On the outside, we put the divisor. On the inside, we put the dividend. So the top goes on the inside, the bottom goes on the outside. Now let's divide. Now remember, with long division, if I were dividing, let's say, 10 into 427, I wouldn't just try to see how many times 10 goes into 427. I'd break it into smaller pieces. Instead of looking at 427 completely, I'd look to see, does 10 go just into 4? And then I'd say, how about 10 into 42? And then I'd say, well, 10 goes into 42 4 times with a remainder. And then I'd put the 4 on top, multiply it, put the product on the bottom, subtract, and then go through lather, rinse, repeat over and over and over again until I run out of terms. Same basic idea here. We're not going to look at the entire 3x plus 2. We're just going to focus on the front end, 3x. We're not going to look at the entire dividend. We're just going to focus on the front end, 3x cubed. And I'm going to ask myself, how many times does 3x go into 3x cubed? Now, of course, when these are just numbers, when these are just real numbers, it's a little bit easier. How many times does 4 go into 12? Well, 4 goes into 12 3 times, because 4 times 3 gives us 12. 3x into 3x cubed, I often hear incorrect responses of 2 times or 3 times, depending on how well you understand exponent properties, because of course I've got x to the first and x cubed, so I can fit in, I can add 2 more to the exponent and get x cubed, or I can say I can 1 times 3 and I get x cubed. But when you respond like this, you're misunderstanding what's going on here. When I say how many times does 3x go into 3x cubed, I'm asking 3x times what would give us 3x cubed. And at that point you might realize, well, I'd have to multiply times x squared. So 3x goes into 3x cubed, x squared times. Now another way to look at this is to say, well, how many times does 3x go into 3x cubed? Well, what we're really doing is dividing. So what I can do is just ignore all these terms, ignore this term. What I'm really doing is 3x cubed divided by 3x. And if I think about it like that, ignoring everything that I'm not really needing to worry about right now, I can very quickly come up with x squared. Now notice where I put the x squared, I like to line up my terms. It helps me be consistent throughout the problem. So I put the x squared on top of the x squared term. So then I've got my number up top. What I'm supposed to do is take the number up top and multiply times the entire quantity right here. So I'll do that one piece at a time. X squared times 3x gives me 3x cubed. Stick it under the other cubic term. X squared times 2 gives me 2x squared. Stick it under the x squared term. Always keeping sure my terms are lined up. So I figure out the term up top, multiply, and then subtract. Now remember, when you subtract, you're subtracting everything in that line. Don't just subtract the first term, subtract everything. We talked about this back in section 1.4. When we were subtracting a quantity, that negative has to be distributed. So it's 3x cubed minus 3x cubed. Those are going to cancel out, and yes, they will cancel out every single time. And then 5 minus 2 gives me a positive 3x squared. Once I've got that, I bring down the next term and lather, rinse, repeat. Do it all again. Instead of doing 3x into 3x cubed, now we're going to do 3x into 3x squared. So I can just divide 3x squared by 3x. That means 3x goes into 3x squared x times. So I'll stick the x up top. Multiply and subtract. And I end up with 6x. Bring down the 7, lather, rinse, repeat. 3x into 6x, well, that's just going to be 2. So multiply and subtract. 7 minus 4 is going to give us 3, and I don't have any more terms to bring down, which means I'm done. I can't go any further. This 3 would be our remainder. So our final answer would be x squared plus x plus 2. Now, the way you write the remainder, you may have learned in a previous class just to write something like, x squared plus x plus 2, and then either like the actual words remainder 3, or maybe a capital R3, the R representing the remainder. But again, this is an upper level math class. We want to make sure we're using mathematics as our answers, and we're not responding with just, oh, and the remainder is 3. When a remainder is something that was unable to be divided. So if you think about 12 divided by 9, 9 goes into 12 one time and a remainder of 3. So you could write that as a mixed number, 1 and 3/12. The 3 is a remainder. It could not be divided, so it's still over 12. And it's the same sort of concept here. You can think of it, our answer is going to be a mixed number. This would be like the whole number. And then 3 over 3x plus 2 is going to be the fractional portion, the remainder portion of our real number. But what mixed numbers are and what some people misunderstand mixed numbers to be, mixed numbers are an addition problem. When I say 1 and a half, I really mean 1 plus 1/2. So when we write our answer, make sure you put a plus sign between the quotient and the remainder fraction. Alright, so let's do it again. This time, try this on your own. Hit play when you're ready. Feel free to hit play once you've got your setup. There's a common place to get stuck on this one. Feel free to hit play a little bit early. But then as soon as if you get stuck, as soon as you find your way, hit pause again and try the rest on your own. Alright, so once again, top goes on the inside, bottom goes on the outside. So we're going to say x squared into 4x cubed, or you can think of it as 4x cubed divided by x squared. That's just going to be 4x, so I'll stick it right here. Multiply and subtract, but when I multiply, 4x times x squared would go right here. 4x times negative 1, that's just negative 4x. Don't put it right here. It doesn't match with the term above it. Put it right here where it matches. So when we subtract exactly what we see. So 4x cubed minus 4x cubed is going to cancel out. That's gone. Now when we get to the 3x squared, notice there's nothing here to subtract, but there's always something. We can always put in a placeholder. Let's just put in 0x squared as a placeholder. Anytime you've got a missing term, that means you have 0 of them. Feel free to use a 0 as a placeholder. That's going to be a common theme throughout. Keep that in mind. So negative 3x squared minus 0 is still negative 3x squared. Negative 4 minus negative 4, well, that's going to cancel out. You're left with 0x. And then we'll go ahead and bring down the 3. So once again, x squared into negative 3x squared, well, that's easy. That's just going to be negative 3. So multiply and subtract. Negative 3 times x squared is negative 3x squared. Negative 3 times negative 1 is positive 3. Once again, we've got a missing spot, so I'll just go ahead and put a 0x as a placeholder. And negative 3 minus negative 3 is going to cancel. That one's going to cancel. And hey, this is going to cancel as well, so we have a remainder of 0. So this time we have an exact answer of 4x minus 3. Now let's talk about synthetic division. So here's a problem I worked out on my own. I had 2x cubed minus 3x squared minus 5x minus 12 divided by x minus 3. Did all the work, had 0 remainder. My exact answer was 2x squared plus 3x plus 4. Now the division algorithm is kind of a beautiful thing. It keeps track of things even without you even thinking about it. For example, the variables, x cubed, x squared, x, and the constant. The variables themselves, as long as we write it in the correct order, really don't need to be there. It's just like writing a number, 427. I don't have to say that 4 really represents 400, even though it does. The 4 in its location represents 400. 2 represents not 2, but 20. 7, though, represents 7. We have a place value system. That way we don't have to come up with an infinite number of digits to represent every single number. We can just use 10 simple digits to represent any number that we want to. Kind of an ingenious idea that early mathematicians or early civilizations came up with. And the division algorithm, polynomials, you can actually work out the same way. X cubed, x squared, x, and the constant. This is kind of like a place value system. So I could really just, as long as everything's written in order, I can ignore the variables completely without losing any real meaning. For that matter, I can also ignore the fact that the 2's are going to cancel, the 3's are going to cancel, the 4's are going to cancel. What's really important in this algorithm are these numbers right here. The -6, the -9, the -12 really dictate what that next row is going to look like. So if I only keep the numbers that I need, again, the -6, the -9, the 12, the numbers I started with, the answer, and what I'm dividing by, I get something that looks like this. And this hopefully is what you recall as the synthetic division algorithm. Now, notice when the 2 just drops straight down, but -3 and -6, I would have to subtract to get 3. I would have to subtract to get 4. I would have to subtract to get 0. So in order to simplify things, instead of using -3, which remember the -3 came from x minus 3, instead of leaving it as a -3, let's change it to a positive 3. In other words, let's change it to the root of x minus 3. If I change this to a positive 3 and also change all these numbers to positive numbers, then instead of subtracting to get the bottom row, I can simply add. Again, 3 was the root of the divisor, and I can add straight down to get from my original function to my new function. Now, hopefully, again, you recall that to get these numbers without doing all that long division algorithm, it's simply 2 times 3 gives you 6. 3 times 3 gives you 9. 4 times 3 gives you 12. So we still have the answer multiplied by the divisor technique, just a little bit in a different format. So again, whatever we get down here gets multiplied up here, and the answer goes over here. And of course, that last number still represents the remainder. So let's look at the first problem together, and then I'll give you the second two on your own. So here we have x to the fourth minus 10x squared minus 2x plus 4 over x plus 3. So we start with our basic format. And again, the variables are irrelevant. We just use the numbers themselves. We'll start on the outside. Remember, it's not 3 that goes here. It's the root of x plus 3. So if I set the bottom equal to 0 and solve, I get -3. So I'm going to put -3 on the outside. I'm dividing out -3, not +3. And on the inside, I don't need the whole polynomial. I just need the coefficients. So I'm just going to list out the coefficients. Starting with x to the fourth, the coefficient is 1. But then I realize x cubed is missing. We have a missing term. Now remember, think of it like a place value system. The difference between 427 and 4027 is a missing value. The 0 has to be there to show the difference between 427 and 4027. So since we're missing the cubic term, we'll put a 0 in as a placeholder, and then just continue from there. -10, -2, +4. So this is the quartic term, cubic, quadratic, linear, constant. Now we can just follow our synthetic division algorithm. We start by taking that first term and just dropping it down. So we have a 1 to start with, and then multiply. Put the -3 here, and then instead of subtracting, we are going to add vertically. So 0 minus 3, or 0 plus -3, which is 0 minus 3 gives us -3. Multiply, we get 9. Add, we get -1. Multiply, we get 3. Add, we get +1. Multiply, we get -3. Add, we get +1. And remember that last digit represents your remainder. So now again, we ignored the variables because the algorithm itself keeps track of the variables. All we have to do is figure out what the coefficients are. So these numbers right here represent the coefficients of my quotient. We started with a quartic. We divided by a linear. When I take x to the fourth and divide by x, I'm going to end up with a cubic. Anytime you're doing synthetic division, you're always dividing by a linear function. Therefore, your original polynomial is simply going to be decreased by 1 degree. So if you started with a quartic, that means this 1 should be the coefficient of the cubic term. So then -3 must be the quadratic term, -1 must be the linear term, and 1 must be your constant term. And of course, 1, the remainder, goes over the original divisor, x plus 3. So my final answer, x cubed minus 3x squared minus x plus 1 plus 1 over x plus 3. Much quicker, much more efficient, much simpler than long division. All right, here's another one for you. Hit play when you're ready. So we start off the same way. We'll find the root of 3x plus 2. Hopefully you figured out the root was -2/3. Throw in our coefficients of the dividend, 3, 5, 8, and 7. Now, you probably saw the fraction, got a little worried, but don't worry. These problems are designed to be nice. So when I drop the 3 and multiply 3 times -2/3, hey, 3's are going to cancel. You just have -2. 5 minus 2, once again, that's 3. Hey, 3 times -2/3, that's still -2. 8 minus 2 is 6. 6 times 2/3. Well, remember, 6 divided by 3 is 2. 2 times 2 is 4. So 6 times 2/3 is just 4, or -4 in this case. 7 minus 4 gives us 3, and that, of course, would be our remainder. Now, I wonder, did you realize that this was actually the question that we did first in this lesson? This question right here, we already did. It was the very first thing that we did. And notice, this was not the answer that we came up with. 3, 3, 6 are not the coefficients of my quotient. So what did we do wrong? And my answer is nothing. We just misunderstood what it was that we were dividing by. Here's the caveat of synthetic division, the one that you were probably told in Algebra 2. Synthetic division only works when you're dividing by something that's of the form x minus a. So the x, the linear term, has to have a coefficient of 1 in order for synthetic division to work. That's just the way synthetic division is designed. So you were probably told in Algebra 1 that for a problem like this, you have to do long division because the linear coefficient is not 1. On the last problem, it worked just fine because the linear coefficient was 1. We got our answer straight away. On this one, the linear coefficient is 3. Your Algebra 2 teacher probably told you just use long division because synthetic division is not going to work. But synthetic division does work. When I divided by -2/3, -2/3, that's what you're dividing by. What I really divided by was the factor x plus 2/3. So I divided by the linear factor with a coefficient of 1, x plus 2/3. So really what I'm doing, I just have to think of this rewritten. Think of that 3 and pull it out. If I were to factor out that 3, factoring something out means dividing. Factoring out that 3 would turn that 2 into 2/3. When we divided by -2/3, as far as the algorithm was concerned, I was dividing just by this factor, x plus 2/3. That's where the -2/3 came from. So the answer I have right here, 3, 3, 6, really comes from just dividing by this. So in other words, I have yet to actually divide by 3. It's just like if I gave you 40 and said divide by 8. Sure, I could divide 40 by 8, but couldn't I also divide 40 by 2, by 2, and by 2? So sometimes when numbers that we're dividing by are too large, simply break it into smaller pieces. 40 divided by 8 is the same thing as saying 40 divided by 2, divided by 2, divided by 2. It's the same thing here. This function divided by 3x plus 2 is the same thing as saying this function divided by x plus 2/3, and then again dividing that answer by 3. So that's what we're going to do. We're going to divide the 3, and the 6 by the coefficient of the linear term. Anytime you have a coefficient of the linear term, just go ahead and divide that extra as a last little bit. Notice I'm not dividing the remainder because the remainder is something that was not able to be divided. So it's going to be over the 3x plus 2 in the end anyway. We only have to divide the proper quotient, not the remainder. So we get our answer, which is the same answer that we got before. So here's another one. once again, we're dividing by x squared minus 1. We're dividing by something that's not linear. But in the same concept that we did before, we're simply dividing by something too big, so break up what that is that we're dividing by into smaller pieces. X squared minus 1, can't that be factored? That's really x plus 1, x minus 1. So what we're going to do, just like dividing by 8 really means dividing by 2, dividing by 2, divided by 2, we're going to do synthetic division, but we're only going to do one factor at a time. It doesn't matter which one we do first because it's commutative. We can do it in either order. So basically, I'll take the top and divide by x plus 1, and then I'll take that answer that I get and divide it by x minus 1. So why don't you go ahead and give it a try, dividing by x plus 1, and then hit play when you're ready. So x plus 1 gives me a root of -1. I populate with my leading coefficients. I populate with my coefficients 4, -3, -4, and 3. Go through the process, drop the 4, multiply and add, multiply and add, multiply and add. So I have a remainder of 0. Now the next step is to simply divide by x minus 1. Basically, I'm going to pretend like this is my top row, so this row would represent this row right here, and I'm going to divide by positive 1, and I'm just going to do it again in a successive order. So go ahead and try this, hit play when you're ready. So once again, we'll drop the 4, multiply and add, multiply and add. Now in this case, multiplying 0 times 1 would just give me 0. There's no need to do this row right here. I can go ahead and stop right here. So notice, we have 4 and -3. So this time, this 0 would represent my remainder, my final remainder. I started with a cubic, so this 4 represents the cubic coefficient. When I divide it out, I got this 4, so this 4 represents a quadratic coefficient. But then I divide it again, so this 4 represents a linear coefficient. So 4 and -3 produces 4x minus 3. And once again, we've done this problem before. Look back in your notes. This was the second problem that we did when we divided by x squared minus 1, and we got an answer of 4x minus 3. So this goes to show that we don't have to do long division. We can always do synthetic division. We just have to be creative with our application of synthetic division. If you have something other than a linear factor in your denominator, simply factor it out and divide one factor at a time. If you have a leading coefficient on the x, don't forget that that leading coefficient represents its own factor and should be divided when you're done. All right, let's go on to the remainder theorem and the factor theorem. So the remainder theorem starts with the concept of I take a function and I divide by a linear factor x minus a. When I divide, I get a quotient, and sometimes I get a remainder, and that remainder is simply written over the x minus a. So this format is simply the format in which that we rewrite our answer. We've got our dividend divided by a divisor equals a quotient plus a remainder over the original divisor. Now, this is kind of a cumbersome way to write a division problem. Notice that we have x minus a in the denominators on both sides. We could simply multiply everything times x minus a to cancel out those denominators, and we'd get something like this. Notice the quotient would have to be multiplied times x minus a since there's not an x minus a for it to cancel with. So this is just an alternative way to write the answer to a division problem. So f of x is really just x minus a, its divisor, times the quotient plus a remainder. Now imagine I wanted to evaluate this function at whatever that a value was. So if I plug in a for x, then I'd have to plug in a anywhere I see the x. So notice a minus a, that's just 0, which means this entire term cancels out. So if I evaluate a function at the a value, which is the root of what I'm dividing by, that's the same value as whatever the remainder was when I divided, which is the remainder theorem. The remainder theorem says if a polynomial is divided by x minus a, then the remainder r is equal to the function value at a. So this allows us two things. It allows us to, option 1, evaluate a function without actually evaluating it. I can simply divide, figure out what the remainder is, and that represents the value of the function. So if I have a really long polynomial that I really don't want to have to evaluate all those exponents on, I can simply ignore the variables, do synthetic division, figure out what the remainder is, and that's the value of the function. Or for that matter, I can figure out what the remainder is, simply by evaluating the function. So if evaluating the function is easier, I'll evaluate the function. If doing synthetic looks easier, then I'll just do synthetic and get the remainder. So here's an example. Given this function right here, we've got a quartic function with some large coefficients. Evaluate f of -2. So again, I could simply take -2 and plug it in for x. Now if I have a calculator, this isn't that big of a deal, but if I don't have a calculator, that's a lot of calculations that I'm going to have to do. Maybe it would be easier to multiply and add, multiply and add, multiply and add, do synthetic division, figure out what your remainder is, because the remainder is equivalent to the value of the function. So that's what we're going to do. We're going to divide out. Now here's the tricky part. Are we dividing out -2 or +2? Remember, we're dividing out the a value, whatever the a value is, x minus a. So in this case, -2 is the root that which I'm dividing out. It's not written as a factor x minus 2, in which case the root is +2. It's written out -2 as a root itself. So let's just go ahead and run through the synthetic division. Drop the 2. 2 times -2 is -4. Add and multiply, add and multiply, add and multiply, add, and we get our remainder of -4. So that remainder, all this work was to get to the remainder, is the value of the function. F of -2 is -4. Feel free to confirm this. Simply plug in -2 into your calculator. Remember on the 8384, use the store feature. Store -2 for x, and then type out this function. Hit enter. You should get -4 as your answer. Here are 2 more. Why don't you give these a try? Hit play when you're ready. So once again, the root that we're plugging in is 2. So we'll drop the 2, multiply and add, multiply and add, multiply and add, multiply and add. Notice this time we get 0 as our remainder, therefore f of 2 equals 0. Here's another one. If you haven't already done this, pause here and then hit play when you're ready. So once again, populate our numbers. Notice again we've got missing terms, so we got to throw in some zeros anywhere there's a missing term as a placeholder, and we're going to divide out +2. Drop the 1, multiply and add, 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 and multiply and add. So we get 14, which is the value of g of 2. And finally, the factor theorem, which itself is a logical extension to the remainder theorem and leads us directly into the rational root theorem. Once again, here's that division statement. Function divided by something equals a quotient plus a remainder, and of course it can be rewritten like this. Now imagine, what if that remainder was 0? What would that mean? If r equals 0, that means we could rewrite our answer like this, something times something. So if the remainder is 0, there's nothing being added to the end of this product, that means x minus a and the quotient are themselves factors of the original function. So by dividing out x minus a, finding that the remainder is 0, that tells me that x minus a is a factor of f. That tells me that the quotient is a factor of f. So the factor theorem says that a polynomial function has a factor x minus a if and only if the value of the function at a is 0. So if it's a factor, then f of a should be 0. If f of a is 0, then x minus a must be a factor of that function. So if I ask you, hey, is x minus a factor of this function? We can simply, once again, either evaluate the function f of a, or since evaluating and synthetic division tell us the same thing, we can use synthetic division to figure out if the remainder is 0. If it divides out evenly, then it's a factor. So let's look at these 3 problems. Now, hopefully you notice something familiar about these 3 problems. These are the exact same 3 functions that we did in the remainder theorem. Also, hopefully you'll notice x plus 2, x minus 2, x minus 2. If I find the roots of x plus 2, x minus 2, x minus 2, those are the same values at which we evaluated earlier. So we've actually already done the legwork on these problems. So my goal here is x plus 2 a factor of this function. What I'm going to do is I'm going to simply evaluate this function at -2. Or instead of evaluating, I'll do synthetic division and look for the remainder. Since I already did that, I know that the value of the function, or the remainder, is -4. So since the remainder is -4, that means no, x plus 2 is not a factor because it has to be 0. The remainder has to be 0 for x plus 2 to be a factor. Since this one did not divide evenly, then it is not a factor. So look at the other two, recall back to what we evaluated, answer the questions, hit play when you're ready. So on the second one, if you recall, when I evaluated at a equals 2, when I divided by 2, I got a remainder of 0. Since it divided evenly, yes, x minus 2 is a factor. And on the last one, when we divided, we got 14 as our remainder, so g of 2 equals 14. Once again, since it's not 0, then it's not a factor. Now that we've got all the pieces, our next lesson will cover the rational root theorem and take all these pieces and put them together into one big problem. Stay tuned.